Mr. Covey here, and this video is about solving differential equations of a particular type, and this should be a pretty quick video here. So this is on page 14 if you go by the PDF numbering, or 15 if you use the other numbering, in your note packet. And I'd like you to start by just taking a couple minutes here to solve this differential equation using separation of variables. And I want you to get the particular solution. Which solution? The solution that has a y value of -4 when t is 0. So this is what we've been doing the past few days in class. Separate the variables, solve this differential equation. Go for it. Pause and actually give this a try, please. Thank you, thank you. Okay. Before we actually go over the answer, I want you to look at this differential equation and just put on your thinking brain. Yes, your thinking brain. For a second here. This is saying, hey, tell me a function whose derivative is twice itself. Well, that's weird. Like, most functions' derivatives don't have anything to do with themselves like that. You know, your derivative isn't just like twice your original function. It's a particular type of function y that has the property that its derivative is a constant multiple of itself. What kind of functions have this property? Exponential functions. Okay. So I hope you kind of have that idea in your head. If not, put it in there now, and we'll talk more about it. But let's dive into the work here. So first thing we need to do is separate the variables. What does that mean? It means get the y on the same side as the dy and get the t's on the same side as the dt. There are no t's here, but we need to get the dt on the other side. So we do a little cross multiplying. Okay. Once you got the variables separated, you integrate both sides. Okay. Notice this absolute value is here. That's very, very, very important. We'll come back to that in a second. We integrated both sides. We need to put a plus c. I'm going to call it c prime for a reason that I will talk about in a second. Yeah, instead of just calling it c. This is the point when you should solve for the initial condition. It's easier to do it at this point. You don't have to. You can go about getting the y by itself, but it's easier to solve for the initial condition here. What I mean by that is to plug in this point. The output, the y, is -4 when t is 0. In other words, of all the solutions to this differential equation, tell me the one that goes to the point 0, -4. t0 or x0, y -4. Okay. So I'm going to plug that in and I'm going to solve. Math, math, math. I get that c prime is natural log of 4. It's easier to solve for this initial condition here, and then to go back here, plug it in, and solve for y. When you solve for y, well, how do you get the y by itself? You flip it from logarithmic form to exponential form. And then you have to deal with this absolute value. Before we talk about that, I hope this simplifying isn't throwing you off here. I will show you an extra step here in case you're getting thrown off where the 4 came from. E to the 2t plus ln of 4. Well, that's just e to the 2t times e to the ln of 4. Math, exponent properties. What's e to the ln of 4? That's just 4. Okay. Because of that absolute value, though, we need a plus or minus here. And this is important. Okay? Do you use the plus or the minus? You don't use both. So our equation isn't plus or minus. It has one or the other. Well, use the minus. How do you know you use the minus here? Because it has to fit that initial condition. Okay, so never leave the plus or minus in there. Make sure that you're using the one that when you plug in 0, you get out -4. And so this is our solution. You can very easily check that this is the solution. How? Well, you should be able to do the derivative of this. You should get -8 e to the 2t. Oh, the derivative is twice the original. Does it go to the point 0.04? Yeah, if you plug in 0, you get out -4. Okay? So you can confirm that this meets these two conditions. What I really want to talk about today is the fact that because this differential equation looks like this, there's kind of a shortcut. Okay? This totally works. It's something you should be able to do. It's not crazy hard, but there is a shortcut. The shortcut goes like this. I know, pretty good shortcut. Okay, it really does save you a lot of time. And I'll show you. Basically, here's the deal. Don't look at the green, look at this real quick. If you have a differential equation that looks like this, in other words, dy dt or dy dx equals constant times y, the solution is going to be exponential. Why? Because there's not a lot of functions whose derivative is just 6 times the original function. Usually the derivatives are completely different. Think about the derivative of x cubed. The derivative is 3x squared. It's not like 2 times the original, you know what I mean? So if you have a differential equation like this, its solution is always going to be exponential. And we're going to kind of leverage that to help us be able to solve a differential equation that looks like this very quickly. And these are actually very, very common. Why are these very, very common? Look at this word problem right here. The number of bacteria in a population increases at a rate that is proportional to the number of bacteria present. That's just kind of a fact if you think about what it's saying. Okay? The rate is going to depend on how many there are. Okay? And this is describing a differential equation that's going to look like this. Okay? Things, particularly in nature, increase or decrease at rates that are proportional to the current amount. And that's what a differential equation like this is really saying. So these differential equations do show up a ton. They show up a ton in science classes as well. Also business stuff. Anyway, let's dive in. You do not have to write this down. All I want to show you here is I'm going to solve this differential equation in general for any k value. Watch this. Okay, I'm going to do what we just did. I'm going to multiply the dt over, separate the variables. I'm going to integrate both sides. Okay, blah, 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 blah. Math, math, math. I'm going to flip it into exponential forms, exponentiate both sides. I'm going to get something like this. I'm going to take this e to the kt plus c and rewrite it as e to the c times e to the kt. And I'm going to replace that e to the c with a different variable. I'm going to call it a. What is the point of all this? It is to say that anytime you come up to an exponential equation that looks like dy dt equals ky, the solution is going to be an exponential equation that looks like this. Furthermore, that constant out front, and I do want to kind of emphasize, that constant out front, although it's multiplied there, it came from the plus c part of the integrating both sides. It's just that we changed that plus c here to be an e to the c times that, and then we said, I'm just going to replace e to some constant with a different constant. Okay, so differential equations that look like this have exponential solutions. Furthermore, what is this constant a? Well, if you plug in 0 for t, you get out a. In other words, a is like the starting amount, your initial amount. Okay? Summary is this. If you have a differential equation, this is the really important thing. Please write this down, most important thing. If you have a differential equation that looks like this, where k is a constant, dy dx or dy dt equals k times y, then the solution automatically looks like this. The k is the same k. I'll repeat that. The k is the same k. What's the c? Well, that's the initial condition. You will either be given that, in other words, it would tell you when t is 0, here's the y, and you just plug it in, or you're going to have to solve for that. Depending on whether k is greater than 1 or less than 1, this exponential might be growth or decay. Depending on whether the c is positive or negative, this exponential might be flipped, or even decay flipped. So just be aware. Cool. And you can always solve this by separating the variables. You can always do that. This is a shortcut. And it's a good shortcut to know. Because these types of differential equations show up very, very often. I'll give you a super quick example here. Dy dx equals 4y. I walk up to this differential equation and I want to find the particular solution that goes through this point. Instead of separating the variables, I'm just going to say, hey, I know that the solution to this is going to be exponential. It's going to look like this. What's the c going to be? Well, I'm going to plug in this point, 1 for x, 7 for y. I'm going to solve for the c, and I'm going to have my solution right here. Okay. I didn't have to separate the variables. This took me 30 seconds to solve at most. Okay. If you skip down here on your paper, I want to do 2 more problems together. First, let's look at this differential equation. It says dy dt equals 3 times 2 minus y. If you wanted to, you could FOIL that out and get 6 minus 3y dy dt equals that. I want to caution you right now. This looks like a really simple differential equation. This is not, it is a simple differential equation, but it is not the exponential thing. So that exponential, that little shortcut I just showed you, only works when it's constant times y. There's an extra thing here. How do you solve this differential equation? You separate the variables. Okay, so you can only skip the step if it looks exactly like that. Okay, so how do you solve this? Separate the variables. Go ahead and take 2 minutes, solve this. Here's your initial condition. Go ahead and run through this. It shouldn't be too bad. Oh, I do want to emphasize one thing, sorry. Don't distribute it out. It will make separating the variables difficult. Leave it like this. Thank you. Go for it. Separate the variables. Give it a try. Thank you, thank you, thank you. Okay. I hope that wasn't too bad. So you should have separated the variables here. When you integrate both sides, you end up with this line. This is when you should plug in 0 for t and 5 for y and solve for the c. You get negative ln of 3. Plug that back in, and now we just have to go about getting y by itself. Divide both sides by negative 1. Flip it into exponential form. Change that e to the ln of 3 to just a 3 out front. Don't forget about our absolute value. So when we get rid of that, we need to put a plus or minus. Get the y by itself, and then let the initial condition, when t is 0, y is 5, dictate that we want this to be a positive 3. The solution here was still exponential, but we couldn't really use that shortcut in the same way. Okay, we just had to separate the variables. Okay. Last thing is just a real quick word problem. I just want to kind of show you guys this idea. This is not a terribly big deal, I don't think. So what it says is the number of fruit flies in an experiment increases in proportion to how many fruit flies there are. Makes sense. Okay. What that's telling you is something about our differential equation. It's telling you that the amount it increases is proportional to the amount there is. dy dx equals constant times y. We'll talk about that in a second. And it says, hey, 100 flies at time 2, 300 times, 300 flies at time 4. How many flies were there originally? Okay. What I want you to think about is the fact that this first line is telling you that the rate of change is a constant times the original function. Okay. And if you think about this as being f of t being the number of fruit flies at time t, what this is telling you is that df dt, the rate of change of the number of fruit flies, equals a constant times the number of fruit flies. What are they asking us to figure out? Well, they're kind of asking us to figure out the solution to this differential equation, essentially. Because our differential equation looks like this, I can do my shortcut. Whoa! Look at that, that was beautiful. Differential equation, solution. What do I not know? Well, I don't know a couple things in this. I don't know what the k is, but I also don't know what the c is. Luckily, they give me 2 points. Time 2 flies 100, time 4 flies 300. So how do I figure out the C and the K? Well, I plug those 2 points in and I end up with these two equations. Oh, this is just a system of equations. This is all AATH, MAH stuff. Okay, how do you solve this system? Easiest way is just to divide these by each other. Solve for K, solve for C. I'm not even going to do that, but keep in mind that what the question was asking you is how many fruit flies there were in the original population. So they were asking you for the initial amount, which would be C. The only reason I wanted to bring this up was because it's kind of cool to think about a population increasing in proportion to the current amount being a differential equation. That concludes this video. Thanks for watching, guys.